Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Greetings, I'm LeRoy, and welcome to the Natural Physics Experience, live from Costa Rica. We left off with having come to the conclusion that we need to switch coordinate systems. The 2x2 matrix that we have derived by multiplying those 4 2x2 matrices together, right? The 2x2 matrix that represents the radially focusing, axially defocusing component of the quadrupole, and a drift space added to that to give it a physical dimension. This is the thin lens approximation, remember? And then we have the radially defocusing, vertically focusing component. Radially defocusing or horizontally defocusing, axially or vertically focusing component of the quadrupole magnet, right? 4 2x2 matrices that we had to use linear algebra to multiply those 4 together to get a resultant matrix. Let's go to that. Okie dokie. Okay, here we are. These are the 4 matrices I just referred to, all right? And multiplying the 4 together, we get this resultant matrix, okay? Length L being the length of a quadrupole magnet, okay? Now, if you remember back to when we were we were deriving the equations of motion of the protons as they circulated around the synchrotron, the original equations of motion were such that the proton's horizontal or radial position in phase space, right, and its vertical or axial displacement in phase space, both with respect to that z-axis, that central axis, central trajectory through the quadrupole magnets, it was dependent upon time, right? Right? Let's go back to that to refresh our memory. Okay. Here is the position of the protons with respect to time. And what we needed to do, we needed to switch coordinates. We needed to switch reference frames so that this dependence of the proton's position in phase space on time is instead switched to the proton's position in phase space with respect to its distance along the central trajectory through the quadrupole magnet, okay? So here you have the acceleration of the proton expressed with respect to time. And here you have the acceleration of the proton expressed with respect to the distance along the z-axis, okay? So that's what we did. And doing that enabled us to go further. We got the equations of motion for simple harmonic activity, right? Okay, periodic motion, right? Simple harmonic motion. And it was in terms of S, the distance along the central trajectory, the z-axis, not time, S, not T, time, T time, no, not time T, but distance S along that central trajectory. That's what we did. And we got the equations of motion, which are simple harmonic motion, expressed in those variables. And up popped K, the force constant. In simple harmonic motion with a spring, it measures how tight or loose that spring is. In our case, with the quadrupole magnet, force constant K is going to express how tight that magnetic field is or how loose it is, okay? So that's what we did. We had to switch coordinates from time to distance along the z-axis. Okay, so what we have to do now is the same thing. Now that we have our 2x2 matrix from the thin lens approximation that was acquired by multiplying these four 2x2 matrices together, okay? We have the length of the quadrupole magnet, and here comes K again, the force constant of that quadrupole magnet, right? How strong, how tight, or how loose the magnetic force is on the protons, all right? Now, in order to get a starting value for the force constant, we're going to have to do the same thing that we did before with the equations of motion, going from time to S, distance along the z-axis. We're going to have to go from K and L, the force constant K, the length of the quadrupole magnet, which again was initially set at 19.758 meters, all right? Now we're going to have to change a reference frame coordinate system. And remember this phase space ellipse, right? Now we got to go from K and L to phi and beta, right? Phi expresses the angular displacement of the proton in phase space with respect to that central z-axis. Beta is the amplitude, how far out it is. And this is very important to know, right? Quadrupole magnets have a physical dimension, width, height, length. So beta is very important to know. All right, so here we have the equations of motion of the proton in phase space. Its horizontal or radial acceleration with respect to its distance along the central z-axis, okay? And over here, you have its vertically or axially motion with respect, acceleration with respect to that z-axis, that central distance S through the quadrupole. And then once again, you have K. And here, because we made that switch, K is expressed as dependent upon the distance along that z-axis, that central trajectory, okay? You have that for the radial or horizontal direction, the acceleration, and you have for the vertical or axial direction. Now, let's go back. Here, K has not been connected to its dependence upon S. But doing that transition that we did, and as I said, I'm not going to go into that, okay? But using the mathematical tools from our mathematical toolbox, okay? When we make that transition from K and L to phi and beta, it comes out that there's a dependence of the force constant in the axial direction, in the radial direction or horizontal direction, and in the axial or vertical direction, okay? There's a dependence of this force constant on S, the distance along that central trajectory. Think about what that physically means, okay? Now we have found out that the force constant K, how tight or how loose that magnetic field is on the proton, is dependent upon the proton's distance down that quadrupole magnet, that central trajectory. You see how we're finding out a little bit and a little bit and a little bit as we go along? Prior to this transition from reference frames, from K and L to phi and beta, K was a constant. Now we find out it's dependent upon S, the position of the proton through that quadrupole magnet, okay? All right. When we make that transition, okay, the solution to these two equations of motion expressed in the reference frame of S, the distance along the z-axis. When we make that transition to phi and beta, we come up with these two equations, okay? Here, as you can see, we went from the force constant with respect to the distance along the z-axis, both for the horizontal position in phase space, motion in phase space, and the vertical position in phase space. Now we have beta and phi, and both are dependent upon S, the distance along the central trajectory, the z-axis, okay? And we have used more tools from the toolbox, believe you me, trigonometry, algebra, okay? And don't forget, linear algebra is still in the mix with our matrices. So, as before, let me go back here, just as we were able to get the X horizontal, radial, and the Y vertical, axial position of the proton as it goes through the quadrupole magnet with respect to S, okay, the distance along the central trajectory. Now, we have that expressed as the horizontal or radial component X expressed in terms of beta and phi. And the same thing with the radial, with the vertical or axial component of the proton in phase space. It's expressed in terms of beta and phi. So once again, let me just go back. X expressed here in terms of S and the force constant K, of course. And then, okay, X and Y. All right? X and Y expressed in terms of beta and phi. X and Y expressed in terms of K and S, okay? In terms of K and S. So, all right. So, using this, we get a 2x2 matrix that represents a quadrupole in terms of phi and beta. And there's other variables here included, which those are derived from physics and the properties of the quadrupole magnets, the magnetic field. But the point to keep in mind is that now that we went from this 2x2 matrix, right? K, the force constant, and L, the length of the quadrupole magnet, we went from this to this 2x2 in terms of phi and beta. Okay. So again, the elements of this 2x2 matrix, we go back to our phase space ellipse, right? That physically shows what these components mean. And again, remember, this was gotten from the thin lens approximation, all right? But again, the length of the quadrupole, the physical length of it is 19.758 meters. But we use that thin lens approximation to grind that quadrupole magnet down to a filament that really doesn't have a physical length. And then we had to insert the two drift spaces to give it a physical meaning. All right. So here's where we are right now. All right. We have our 2x2 matrix in terms of the phase space displacement and the amplitude. All right. So now what we're going to do, we're going to use that to come up with a real physical number for the force constant K, okay? Excuse the pun. That's what we're going to do. When we come back next week, I am going to provide you with the actual physical number of the force constant, the starting point, and then just a little looks, just a little let you know what's coming up. The computer is going to have to come into the picture, right? We're going to have to use the computer to get that number, to go through all these iterations from the mathematical equations that you've seen, okay? The equations of motion, the matrices. We're going to have to use the computer to get that force constant, okay? All right. Okay. So from what you've seen, we are now at the point, we have a 2x2 matrix that expresses the effect of a quadrupole magnet on a proton in terms of the displacement phi, the phase space ellipse, and the magnitude of that ellipse, beta. So what we did was we went from that 2x2 matrix that we got using the thin lens approximation by multiplying those four matrices together, right? The radial or horizontally and vertically and actually defocusing component of a quadrupole magnet. times a drift space times the radially or horizontally defocusing and vertically or axially focusing component of the quadrupole magnet times another drift space, okay? 4 2x2 matrices, again, using the thin lens approximation. And we got a 2x2 matrix that represents that quadrupole. Now, just as previously, we needed to be able to go from expressing the horizontal and vertical displacement of the proton in phase space with respect to time. Remember how we needed to switch gears and go from that dependence upon time to the dependence upon the proton's position along the z-axis, the trajectory that goes right through the middle of the quadrupole, denoted as S, right? Remember, we had to go from there, from the X and Y displacement in phase space of the proton with respect to time to the X and Y displacement of the proton in phase space with respect to the z-axis. So we had to do the same thing here. Once we got our 2x2 matrix, okay, by multiplying those 4 2x2s together, and it's expressed in terms of the force constant K and L, the length of the quadrupole, we needed to go to another reference frame to expressing that 2x2 matrix in terms of phi, the angular displacement of the proton in phase space, and beta, how far out it is from that central z-axis, okay? All right? That's what we needed to do. So, now that we've done that, we're going to bring the computer in, okay? And we're going to find out what that force constant is. But you see what we had to go through to get here? All the mathematical tools from our toolbox, okay? And now we're about to bring in another tool, right? The computer. All right. Tune in next week. Same fat time, same fat channel.